Welcome back to our series on statistical mechanics. In the last episode, we were evaluating the number of microstates for a classical ideal gas. There, we calculated the total number of microstates, we evaluated the entropy of the classical ideal gas. There, we were stumbled upon one of the paradoxes which we call as the Gibbs paradox. And we found that it is something which the physics cannot admit. Why? Because the entropy is considered to be a extrinsic parameter, but while we calculated or evaluated the number of microstates and after that we went on to derive the entropy of the system, we found that the entropy ended up to be an intrinsic parameter, which is not acceptable. In this episode, we will try to rectify the Gibbs paradox by re-evaluating the number of microstates. So, there if you remember the expression which we found for the total number of microstates which we assumed for the classical ideal gas was omega is equal to V by h cube raised to n 2 pi me raised to 3n by 2 divided by 3n by 2 factorial. V by h cube raised to n 2 pi me raised to 3n by 2 3n by 2 factorial. This was the expression which we use for the calculation of the entropy of the classical ideal gas. There, as I reminded you, we reached the Gibbs paradox. Now, what could be the correction which we could apply for solving this Gibbs paradox? One of the suggestions which we could make is that we could divide it by a number which is n factorial. So, our plan is to divide this omega expression for omega by n factorial. Now, the question is that what is that logic which leads us to think that a division by n factorial could solve this Gibbs paradox, right? So, our plan is to divide by n factorial. So, if you remember, when we started with our discussion on the classical ideal gas, we made two major assumptions. One was that all the particles in this ideal gas system or the box were identical, right? Which naturally led me to think that all the identical particles were distinguishable, right? Basically, that natural thinking comes from our classical way of thinking, right? We think that all these identical particles could be distinguishable. So, like for example, if I have a box in which I divide it into 3 sections and I say I put A, B, C, particle A, particle B, particle C into the different cubicles of this box, I can think that there are 3 factorial different ways of arranging the particle A, B and C in this box. But instead, if I think that these particles are indistinguishable, which means that now I have to fill this box with indistinguishable particles, which means that A, B, C is now going to be replaced by A. How many ways of arranging this these 3 particles in this box? The answer is that there is only one way of arranging, right. So, the moment you took away the distinguishability of the particles, we found that the number of ways in which these particles, these 3 particles could be arranged got divided by the number of particles, which means that in this case it was 3. In our case, if it was n number of particles, we can naturally assume that it could be divided by n factorial. So, that is why we explore the expression which we propose for the total number of microstates in the classical ideal gas being divided by n factorial. So, if after division with n factorial, and if we found that the entropy, as we expect that it should be an extrinsic parameter, if that is getting satisfied, then our logic of division by n factorial will form as the solution of the Gibbs paradox. So, let us try to do that, right. If I modify, now we modify the omega expression, how we divide it by n factorial, and now I can write that expression as equal to v raised to n divided by n factorial h raised to 3n 2 pi m e raised to 3n by 2 3n by 2 factorial, right. So, only thing is that we introduce this n factorial into our original expression, that is all we did. Let me tell you that sometimes this e could be replaced by the u also, depends on how do you define the e or the u, but e and the u represents the same one and the same thing. So, now what is our attempt? We should calculate the or derive the expression for entropy with this expression for omega. If you remember, in one of the previous episodes, we have derived the expression for SEC for the entropy as S is equal to k ln omega. So, substitute this omega into this expression, and then we can calculate the or evaluate the expression for entropy. So, how do you do that? Basically, you put the omega over here, but in order to solve this equation, we need to use the Stirling's formula, which I have demonstrated in one of the previous episodes. Therefore, I am not re-demonstrating over here. So, if I do it here, I will end up in the expression as S is equal to nk ln V by NH cube four pi me raised to 3n by 2 divided by 3n nk ln V by NH cube 4 pi me by 3n raised to 3 by 2 plus 5 by 2. So, this is the new expression which we will get with the new omega or the modified omega which we have assumed. Now, what do you do? So, if this expression, if we want this expression to be proved to be correct, we need to check for the extrinsic parameters, right. So, how did we evaluated that? Extrinsic means we will change to if we multiply the system by x, or in an extrinsic parameter, if we increase a system by x, that means it should be correctly be reflected in all the extrinsic parameters in that expression. So, the v should be changed to xv n should change to xn, n we have e should be changed to xc, right. Yeah. So, what you have to do is that you substitute all these expression, these equations into this expression, right. If you remember, in the earlier without modification, our S was having plus 3 by 2, instead we have to have the 5 by 2 over here, and the in the denominator now we have an n in the additional n additionally over here. So, while substituting, we have to be careful about that, we do not discount on any of those things. So, let us try to put that over there. So, let me try to correct it over here itself, so that so now S dash is equal to x into s, which I can write it as x n k ln x v divided by x n h cube 4 pi m, e should be x e raised to 3 by 2 divided by 3 x n I did so this should be also be divided raised to 3 by 2, which means that yeah. So, this is the expression after substituting for the, after assuming that all our other parameters are extrinsic parameters. So, what is the end product? We can straight away cancel the x over here, and we can cancel the x over there also, which means that now this is x into, yes, because the earlier the problem was that we were not having an n in the denominator. The unmodified original expression for the entropy was not having an n in the denominator. Since now we have a n in the denominator, we could correctly found that S dash is equal to xs, which means that now the entropy turns out to be an extrinsic parameter, which means what? Which means that the assumption that total number of microstates should be divided by n factorial, which was the hypothesis which we made, is correct. It could really rectify the Gibbs paradox. So, many times we tell that originally we over counted the, this is the expression which you will find in the textbooks. Many times we tell that we originally over counted the number of microstates, which was not necessary. Now we can tell that the Gibbs paradox actually arises from or originated from the classical assumption of indistinguishability for identical particles. So, we assume that all the identical particles should be distinguishable, which is not correct. Now, the moment we found out that the identical particles could be considered as indistinguishable, the Gibbs paradox is now being solved. Now, if we put in this expression for the entropy, this was the expression for the entropy, if we put now E is equal to 3 by 2 nkt. So, this is the expression for energy which we straight away assume for any kind of ideal gas. So, if we substitute E is equal to 3 by 2 nkt into this expression, we will evaluate S should be equal to nk ln V by n plus 3 by 2 Nk 2 pi mkt divided by h squared plus 5 by 2 Nk. So, what we did was that we substituted E is equal to energy is equal to 3 by 2 Nkt for the classical ideal gas into this expression, and if we do the substitution and then simplify, we will end up as Nk ln V by N plus 3 by 2 Nk ln of 2 pi mkt by h squared plus 5 by 2 Nk. So, this expression is otherwise known as the Secoute-Tetrode equation. So, basically Secoute-Tetrode equation is the correct entropy for a classical ideal gas evaluated in the statistical mechanical regime. And another thing, another statement which we can now make is that the entropy of mixing, right? If we remember, we calculated we tested the extrinsic characteristic of the entropy using two different methods. One was the entropy of mixing, and then another was that in the entropy of mixing we calculate Si is equal to S1 plus S2, or Si is equal to summation over Si's. So, that is the entropy of mixing. Otherwise, here we tested the extrinsic characteristic of the entropy by multiplying it with X. So, that is the second way of doing it. So, one statement which we can make right now is that the entropy of mixing is positive for dissimilar gases, right. So, dissimilar gases means if you remember, we assumed A, B, C, three different kinds of particles to be the components of the gas. Then our original evaluation was that delta S greater than 0, right. So, in case if you are mixing dissimilar gases, we will still end up as delta S is greater than 0, but that does not have any clash with the extrinsic nature of the entropy, because we are considering dissimilar gases. So, entropy of mixing will be positive for dissimilar gases, but it will be 0 for mixing of similar gases, or we call as the self diffusion. So, in the case of self diffusion of similar gases, the entropy of mixing will be 0. So, what we did was that, if you remember from the first episode, we made expressions for connection between the microstate and the macrostate, and then we evaluated we found out an expression, or derived an expression for the entropy, and then we calculated we proposed three equilibrium conditions. One was for the thermal equilibrium, which we denoted it by the beta 1 is equal to beta 2, and then we discussed the case of mechanical equilibrium, and there we introduced the parameter eta, and then there was the chemical equilibrium, which we evaluated with the expression of zeta 1 is equal to zeta 2, and then we went on to discuss a specific case of the classical ideal gas. So, here we found out that in the classical ideal gas, when we are discussing, we need to clearly distinguish between if the particles in the classical ideal gas are distinguishable particles, or are they dissimilar gases, or is it mixing of the similar gases, or otherwise which we call as the self diffusion of gases. So, now we need to go further in terms of the classical evaluation of the microstate and the macrostate. We need to mature ourselves in terms of the theoretical investigations on statistical mechanics. There we want to propose a new kind of methodologies and the format which could enable us to do more theoretical investigations on the statistical mechanics, which we will continue with the next episode. Thank you.